lesson, we are going to begin exploring exponential equations. So what I want you to do before we get started is look at the warm-up, complete it, and then once you're done, unpause the video to see the answer. The warm-up says, for this recursive rule, starting with -1, add 2 to get to the next term. Write the equation of a line that models the recursive rule. So the equation of the line would be y equals your starting value, which is -1, plus your rate of change, which is 2x. So it would be plus 2 since we're adding 2 to get to the next term. To sketch a graph of the line, you would take your xy coordinate grid, like so. And then you would put a y-intercept of -1 on your graph, and then you would go up 2 over 1, up 2 over 1. You could also go down 2 over 1. So you get your line for your graph that looks like that. And then it asks, what is the starting point? What is the rate of change? Your starting point was y equals -1, and your rate of change was plus 2. So what we learned about in 6.1 is that recursive rules are useful for seeing how a sequence develops and for getting the first few terms. But the problem that arises is what happens when you need to come up with the 50th term in your pattern. And when we were in chapter 3, we found that the graphs of the points formed a linear pattern. So we had these recursive rules and they ended up creating a straight line. And so what we learned was how to write the equation of a line. However, as we saw in 6.1, recursive rules that use a constant multiplier create a different type of increasing or decreasing pattern. It's not a straight line. It is a curve that is either increasing or decreasing. And so what we're going to do is we're going to find out the connection between the recursive rules that we have and exponents. And using this connection, we're going to come up with a new type of equation, and that will allow us to find any term in a sequence generated by a constant multiplier without needing to find all the terms that come before it. In order to do this, we're going to take a look at what's called the Koch curve. And we did not do this investigation in chapter 0. We skipped over that chapter. So this will be a little bit new. But what you need to understand is that the stage, so we're going to have this drawn for you down below. And so the stage 0 figure is a line segment that is 27 units long. Okay, so stage 0 is just this line right here. It's 27 units long. Then what we do is we're going to draw stage 1. And the stage 1 figure has 4 segments, each 1/3 the length of the stage 0 segment. So what you see is, if you look at stage 1, instead of being a line that goes 27 units long, like so, what we have is 4 units. So we go 1/3 of the length of 27, which would be 9 units. And then you add in a bottomless triangle that has sides of 9 and 9. And then you have the rest of your base, which is 9 more units. So essentially what's happening is you're taking stage 0 and you're going 1/3 of the distance down the line and then adding in a bottomless triangle that has the same length as this first piece. So if we wanted to count up the total length in units, okay, so step 2 says to determine the total length of stage 1, we would come over here and we would add up all of these units. So we have 9, 9, 9, and 9. So that would be 36 total units in length. Now, what I would like for you to do is to try to draw steps or stage 2 and stage 3. Okay. So again, remember what you're going to do. You're going to go a third of the distance. So essentially what you're doing is you're taking stage 1 and then you're going a third of the distance, which would be a length of 3, and you would then draw a bottomless triangle that is the same length. So 3, 3, and then continue. So you're going to draw your stage 1 and stage 2 below stage 1. So try to replicate that and then unpause the video and we'll take a look at what it should look like. So I went ahead and drew stage 2 and stage 3. And what you can see is instead of in stage 1 where we had a length of 9 units for each side, it got divided into 3. So we have 3, 3, 3, 3, and so forth. Every side that we have here is 3 units long. So if we look at this, how many sides there are, there's 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16. So there's 16 sides. Each is 3 units long. So if we multiply 16 by 3, we get 48. So we know that there, for stage number 2, there is a total length of 48 units. And then if we look at stage 3, again, we took the second stage and we took each piece and broke it up into thirds. Okay, so I do have one small mistake on here. There should be another piece that goes up and then over right here. So if we look at this, we see that we now have this new shape. And this new shape has a new total length. And each side has a length of 1. So if you were to count all these sides up, you would find out that there's 64 sides. And each one has a length of 1, so there is 64 total units in length. So now we have our total length for each stage number. And then we could continue going, but it gets very tricky to continue drawing stage 4, stage 5, and stage 6, because then you're dealing with fraction lengths and for this each side. So we have this, and again, what we're going to want to find out is eventually what's the total length in stage 4? What's this total length in stage 5? So if we jump down here to step 4, it says to find the ratio of the total length at any stage to the total length of the previous stage. So again, we want to find a ratio of the total length at any stage to the total length at the previous stage. What is the constant multiplier? So if we take a look at this, we'll see if we take the total length from stage 1 and have a ratio comparing it to stage 0, we'd have 36 over 27. So we get 36 over 27. That can simplify into 4 thirds. All right, so it looks like our constant multiplier would be 4 thirds. We could check that. Again, it doesn't matter what stage you take. We could take stage 3, which is 64, and compare it to stage 2, which is 48, and that also simplifies into 4 thirds. So our constant multiplier is 4 thirds. So constant multiplier equals 4 thirds. So now what we want to do is we want to use our constant multiplier from step 4 to predict the total length of this fractal at stages 4 and 5. And so if we wanted to do that, what we would do is we would take our length from step 3, so stage 4 would be equal to, we could take 64 and multiply it by 4/3. And if we take 64 and multiply it by 4/3, we get 85 and 1/3. 85.3 repeating. Okay, and again, how else could we write this? We could have also taken this and said that stage 4 was equal to the initial amount, 27, and we could multiply it by 4/3 times 4/3 times 4/3 times 4/3, and that would give us the same thing, 85.33 repeating. All right, and so what you see is to predict stage 4, the length of stage 4, you could take your initial amount and multiply it by the constant multiplier 4 times. So if you wanted to find stage 5, you could use our number from stage 4, 85.33, but that is, again, that's a repeating decimal, and that would, if we only put 85.3, that would take some rounding into consideration. So we can take the 27 and multiply it by 4/3 times 4/3 times 4/3 times 4/3 times 4/3. Okay, and what you get is 113.7 repeating. And what you start looking at here is you start realizing that you're multiplying by the same thing over and over and over again. And we learned that we can write that expression using exponents. So if you take a look at stage 2, for the length of stage 2, what we notice is that in order to find the length of stage 2, we would take the initial amount, which was 27, and we multiply it by 4/3 twice. Now, we learned that when we multiply a number repeatedly by the same number, we can take that 4/3 and we can write it like this: 27 times 4/3 squared, because 4/3 is in this factored form twice. So because we're multiplying 4/3 by itself twice, we have 4/3 times 4/3, which is 4/3 squared. Now, if you look at step 7, it asks, what about if you are looking at stage 3? Stage 3 would look like this. You'd have 27 times 4/3 times 4/3 times 4/3. And because 4/3 shows up in that factored form 3 times, we have 27 times 4/3 raised to the 3rd power. So what we have is we can see that if we want to find the length of any one of these stages of the Koch curve, that we can take the initial length of 27 and multiply it by 4/3 raised to the power of whatever stage we are in. So if we wanted to look at step 9 here, it says use an exponent to write an expression that predicts the total length of the stage 5 figure. Evaluate this expression using your calculator. Is the result the same as you predicted in step 5? So is it the same as this? So if we wanted to write this for stage 5, we'd have stage 5 is equal to our initial amount times 4/3 raised to the 5th power. And it does in fact come out to be 113.7 repeating when you type it into your calculator. So it is the same as our prediction from step 5. So the question is, can we write an equation that models the total length of this fractal as a function of the stage number? Then we want to graph our equation and check that the calculator table contains the same values as your table. So if we wanted to come up with an equation that represents the length of the fractal as a function of the stage number, what we would have is y is equal to our initial amount times our constant multiplier raised to the x power for whatever stage number we're in. Okay, so x x equals the stage number. And so if we graph this, I'm going to jump over to Desmos. We have y equals 27 times 4/3 raised to the x power. All right. And if we go over here and we take a look at, let's zoom out a little bit so we can see what this looks like. So here's our graph. And I'm going to adjust this so we have, let's go, we only need to look at, let's go -5, we'll go to 30, count by 5s. And on the y-axis, we'll go from -5 to, we'll go up to 100, count by 5s. So if you look at this, we want to know, is this equation actually the correct equation, all right, as we think it is? So if we take a look at this, we can turn this into a table by hitting the settings button and convert to table. And what you'll see is stage 0. You could ignore we'll talk about this here in a second. Stage 0 is 27. And if you go back to our table, we had stage 0 was 27. Stage 1 would be 36. So there's 36. Stage 2 is 48. Stage 3 would be 64. Stage 4 is the 85.33 repeating. And then we have 113.7 repeating. And so what you'll see is that these numbers are in fact the length that we predicted using our constant multiplier in step 5. So this graph does appear to be the same, the correct equation to represent our data. Now, one thing to talk about, when you see x is -2 and you get 15.1875, in this problem, x being -2 and x being -1 doesn't really apply to this problem because we cannot have a negative first stage or a negative second stage for the Koch curve. Another thing that you should pay attention to is that you see that we're counting by whole numbers. We have 0, 1, 2, 3, 4, 5. We don't have 2.5 or 3.5 in our table right now. Those numbers, if I were to put 2.5 in, it would give us a number. It would say 55.425, whatever, and it pops up on our table right there, there, and it pops up on our graph. But one thing you should pay attention to is in this problem, this doesn't necessarily apply because you cannot have a 2.5 stage figure. So in this problem, we are focused only on our whole number stages. So we'll take that off of there. Now I'm going to screenshot this and toss it into our notes. So there we go. And then, well, I might not be able to, I guess, because this is on my iPad. But we have that graph there, and we were able to see that the table does contain the same values as what we found in our investigation. And so for step 11, it does ask you, what does the graph tell you about the growth of the Koch curve? And what we find is that the growth increases very rapidly. Okay, and that's typically what we're going to find when we're dealing with these exponential equations, is that the growth is going to start off slower than you might think, and then all of a sudden it just increases very, very rapidly. So a recursive rule that uses a constant multiplier represents a pattern that increases or decreases by a constant ratio or a constant percent. Now, because exponents are another way of writing repeated multiplication, you can use exponents to model these patterns. So if you look at this picture right here, you'll see that we have y is this is the equation from step 10. Y is our total length, and then we have our starting value, which was 27, multiplied by our constant multiplier, raised to x, which represents our stage number. And equations like this are called exponential equations because a variable, in this case we used x, appears in the exponent. So when you have a variable in the exponent, that means you're dealing with an exponential equation. And the standard form for an exponential equation is y equals a times b raised to the x power. Now, when you write a repeated multiplication expression to show each factor, the expression is written in expanded form. So that is what we were doing when we were writing 27 times 4/3 over and over again. And since the factor 4/3 occurs 3 times, we can say that 4/3 is raised to the third power. So when you get your equation written in exponential form, you're going to have your starting value, and then you're going to have your constant multiplier, which is referred to as the base. So your constant multiplier is going to be the base, and then the exponent represents the number of times that you're multiplying by the factor of 4/3. Okay, so you have your starting value, which is the letter represented by the letter A. You have your base, which is represented by the letter B, and then you have your exponent, which is x. So let's take a look at a few examples. In this first example, we're going to practice just by taking each of these expanded forms and writing them as an exponential form. So if you look at this, we are multiplying by the factor of 5, 1, 2, 3, 4, 5, 6 times. So this would be equivalent to 5 to the 6th power. The next problem says 3 times 3 times a bunch of 2's. So because we're multiplying by 3 twice, we're going to have 3 squared times 2, and then 2's being multiplied, we're multiplying by the factor 2, 1, 2, 3, 4, 5, 6, 7, 8, 9 times. So it's 2 to the 9th power. And this would be your final answer. You cannot combine these. Okay, you cannot multiply 3 squared times. You can't write this as one exponential form because you cannot combine exponential forms. Cannot combine exponential forms that don't have the same base. Okay, so because our base is 3 squared and our base is 2 and then to the 9th power, because 3 and 2 are not the same base, we cannot combine them, so we just leave it as an expression written like that. Then in part C it says the current balance of a savings account that was opened 7 years ago with $200 earning 2.5% interest per year. So if we think about this, we want to write this in this expression in exponential form. So exponential form, again, remember, is going to be our starting amount. Then we're going to multiply by our constant multiplier with an exponent that represents, in this case, that represents the number of years. So if we look at this, our starting amount would be $200. So we have 200, and then we're going to multiply by our constant multiplier. Our constant multiplier, it is earning 2.5% interest per year. So we are going to have to, since the amount is increasing by 2.5%, we'd have 1 plus 0.025. So we have our constant multiplier 1 plus 0.025. And then we'd raise that to the 7th power because it happened 7 years ago. Now, you could write this as 200 times 1.025 raised to the 7th power. Those two things are the same. Now, the next example says Seth deposits $200 in a savings account. The account pays 5% annual interest. Assuming that he makes no more deposits and no withdrawals, calculate Seth's account balance after 10 years. So we want to let's first come up with an equation that represents the amount of money in Seth's account. So Seth's account the amount in there would be equal to the amount that he put in there. So he put $200 in his account. And then his account is increasing by 5% annual interest. So that means that the amount in his account is going up by 5%. So 5% written as a decimal would be 0.05. So we'd have 1 plus 0.05 because the 1 represents the 100% of his money that's already in there plus the 5% of what's in there. And then this interest is being earned every year, so we'd raise it to x, where x equals the number of years. So again, we have his initial amount times his constant multiplier. His constant multiplier is the annual interest that is earned. And then in this case, we want to know how much money he would have after 10 years. So we'd take y equals 200 times 1.05, because 1 plus 0.05 is 1.05, and we'd raise it to the 10th power. And if we type that into our calculator, we'd get 200 times 1.05 raised to the 10th power, which would be $325 and 78 cents if we round. So after 10 years, there's $325.78 in his account. Now, amounts that increase by a constant percent are called exponential growth. And anytime that we have an exponential growth, it's going to be represented by the equation y equals a times 1 plus 5, or 1 plus r raised to the x power. A is the starting value. R is the rate of growth written as a positive decimal. And then x is going to be the number of time periods elapsed. And y is the final value. Okay? So again, anytime that you want to write an exponential growth equation, it's going to be y equals your starting value times 1 plus your rate of growth written as a decimal raised to the x power. If you wanted to model something that was decreasing by a constant percent, the equation would be similar, except you can probably guess it'd be y equals a times 1 minus r to the x power. So if we look at these two summary questions, the first thing says, how can you find the exponential equation from the recursive rule? And then the way you do that is that in your recursive rule, your exponential equation is going to be y equals a times b to the x power. And what you get is a is going to be equal to your starting value from your recursive rule, and b is going to be equal to your constant multiplier that you get from your recursive rule. All right. And that gives you your equation y equals a times b to the x power. The second one asks, why is the equation exponential? And the reason that it is exponential is because it represents repeated multiplication. Now, we'll take a look at a few more examples. In the first example, it says, write the equation that gives the same value as the recursive rule. So the way you read this, what it's saying is your starting value is 2.1, your recursive rule is 0.1. So what we would have here is we'd have 2.1. This is growth because our constant multiplier is positive. So we'd have y equals our starting value, 2.1, times 1 plus our constant multiplier, and then we'd have raised to the x power. And you could also rewrite that as y equals 2.1 times 1.01 raised to the x power. So either one of those would be correct. In step 2, it says the following equation gives you the balance of an account after any number of years. Give the starting balance and the rate of growth per year. So the starting balance is 1,000, and the rate of growth comes from right here, 1 plus r. So r is equal to 0.02. So our rate of growth would be equal to 2%, because you take your decimal and you move it 2 places to the right, which gives you 2. In step 3, it says write out each term of the sequence 2, 3, 4.5, 6.25, 3.375 as the initial term repeated multiplication of a constant multiplier. So what we would need to do is we would need to figure out what our constant multiplier is. So to figure out our constant multiplier, we would need to take any two terms. So we'll do 6.25 and 4.5, and do 6.25 divided by 4.5. So 6.25 divided by 4.5 gives us a constant multiplier of, let's do 3 divided by 2. So we have 3 divided by 2, which gives us 1.5. All right, and so our constant multiplier is 1.5, and so what we would have, if we wanted to write this out, we'd start with our initial term. We'd have 2 times 1.5 to give us 3, and then we'd have, to get 4.5, we'd have 2 times 1.5 times 1.5, and then we'd continue on going 2 times 1.5 times 1.5 times 1.5 in order to get 6.25. And then if we want to write this as an exponential equation, an exponential equation, what we would have is we'd have 2 times 1.5, we'd have 2 times 1.5 squared, 2 times 1.5 to the third power, and so forth. So what you're going to do is you're going to go ahead and begin working on your homework. If you have any questions, message me on Remind or email me, or feel free to ask questions at the next class.